I will move the, okay, I will move my screen here. Professor, I think we are ready to start. Karina, let me know when we are live so we can start. I will move the, yeah. Okay. I'm looking for the screen of Professor Morgenstern.
We are in YouTube.
Yeah, I cannot find Professor Morgenstern. Okay, no, not yet. Is Professor here? Maybe he disconnected by mistake. Or no?
Yeah.
Professor disconnected, Karina? Maybe.
Parece que...
Okay. He will come back. Por mientras le podemos dar la bienvenida a todos y todas las colegas que están hoy día acompañándonos. Muchas gracias por acompañarnos el día de hoy, tanto en la transmisión Zoom, así como en la transmisión YouTube, en este muy entretenido e importante seminario para la comunidad geotécnica. El día de hoy tenemos la suerte de contar con una figura legendaria de la ingeniería, reconocida no solamente por el mundo de la ingeniería geotécnica, sino que también por todo el mundo de la ingeniería civil en general, por los tremendos avances que el profesor Morgenstern hizo en lo que respecta a estabilidad de taludes, relaves, comportamiento de arena. Ahora me voy a cambiar al inglés para recibir al profesor Morgenstern, que ahora efectivamente se pudo conectar nuevamente, había perdido un poquito la señal. Professor Morgenstern, hello.
Hello.
How are you?
Good. Can you hear me properly?
Yes, I can hear you very well.
Thank you.
How are you in Canada?
I'm fine, Ken. Thank you. It's a nice day. The sun has just come out. The rain has stopped.
Yes, but the weather is getting better and better, right?
Yes. We are. The winter is behind us. We have some flowers in the garden now.
And the city you are living in, it's a beautiful city.
I live in a small town in the Rocky Mountains near Banff, which is a famous place for visiting, and we're close to Banff.
I see. So, well, thank you very much for giving us your knowledge and sharing what you know and all your expertise and experience in this presentation for the Chilean community of geotechnical engineering. We are all very glad that you can have time to spend with us during these coming 2 hours. We really appreciate it, and we really appreciate the opportunity that this is a very special talk for you, right?
Yes, it was given 1 month ago, actually, in Edmonton. Kind of my end of career talk, maybe. We'll see.
After 64 years of practice.
Well,
research, practice, teaching.
Yes, exactly. That's right.
So, is it okay if we make some little questions for you?
Of course.
Before starting with the talk?
We're all friends. We all share common interests, of course.
How is it that you became a geotechnical engineer? What a friend you admire geology? How Professor Morgenstern became Professor Morgenstern?
It's amusing, actually. I was born in Toronto, went to the University of Toronto for my engineering degree, and the Department of Civil Engineering there was very strong in structural engineering at the time, and I hated it. And I was wondering how am I going to get out of civil engineering? Those are the days in which it was pre-computer days and all of that. You did the detailed design. Drawings were in India ink. It was very strict in that regard. And you used the handbook a lot. And I didn't really feel very comfortable. I thought I would end up designing details of steel connections for the rest of my life for the railroad or something like that. So it was this last year.
I understand.
And it was this summer before my last year. I was working on a construction site in northern Ontario, doing survey work, checking bolts and foundations, nothing advanced, of course. I was still an undergraduate. I used to go to the library every couple of weeks. And I came across one time a book called Foundation Engineering by Peck, Hansen, and Thornburn, a classic in our subject at the time.
Oh, that's a great book, actually. Very
Exactly.
nice book.
And
I love it. I love it. It's a classic. It's a must.
I
It's a
took it
must have.
out of the library to read, and I said it was extraordinary. I always liked geology, and this was something to do a little bit with geology. Had a little bit of mechanics, and it had I had no soil mechanics at that time in my career, so that whetted my interest in soil mechanics, which was going to come in the final year of the curriculum. Ralph Feck used to like this story a lot. And I paid a lot of attention to soil mechanics in my final year. And we had a teacher of not great fame, but very dedicated to quality teaching. He allowed me to help him in the laboratory doing routine testing and so on, which he did a little bit. And that basically whetted my interest in the subject. And
I see.
And at the end of the year, I was beginning to make applications to graduate school because I thought I'd learn more. We only had one course with soil mechanics and some foundation engineering. And I also was eligible for a scholarship to go to the United Kingdom. And I was applying to well-known schools like MIT and Harvard at the time, but the prospect of going and traveling in England was the enticing thing. And when I got the scholarship, I went to London and went to Imperial College, not knowing, it was an accident, not knowing that I was going to one of the emerging leading institutions in the world for my studies. So it was, let's say...
oh, you didn't know?
I didn't.
You didn't know?
I knew about the American schools, but I didn't know how leading Imperial College was at the time. So it was good fortune and an accident that got me into soil mechanics, geotechnical engineering. At the
a lucky accident.
A lucky accident.
A lucky accident.
So
I see. So after so you went to UK, and then
went to UK for my PhD, and then went on the staff of Imperial College after 4 years of postgraduate studies.
I see. And you work with Professor Bishop?
Yes, he was my supervisor, and then I was on the staff with Bishop and Skempton and Henkel and Gibson and so on until I returned to Canada at the end of 1968. So I spent many years, formative years, in the Imperial College group.
I see. I see. So, and you moved to Canada back?
I came back.
And you were already working on the slopes, right?
Well, I had already finished my PhD on slope stability.
Exactly.
Was established at least as a bright young academic. I had, by that time, was collecting a little bit of experience in consulting and helping Skempton and Bishop sometimes on their projects. So that was the formative years that began, I guess, 1960 is when I went on the staff, and that's the beginning of this story of 64 years.
I see. So in all these 64 years of practice and teaching, consulting, because it's been a a career in which you have been colored by different practices, different countries, different cultures of geotechnical engineering also.
Yeah.
So um, is there any anecdote or memory that you can share with us from maybe a particular project or a research project that you can share?
Well, the lecture that's coming up is going to be the history of the mistakes that I made and mistakes that other people made, which made the transformation from being certain, which you are as a young academic, you know what to do, you've been taught what to do, to becoming uncertain as you find the challenges of uncertainty in our practice. So I think the stories will unfold through the lecture that's forthcoming.
I see. So yeah, uncertainty it's a huge topic these days. It's a huge topic.
Well, that's the last 10 years I've been involved in some of the tragic failures in mining dams and other dams. And obviously, I don't mean failures because people were working without resources, but people didn't know enough. So the issue of uncertainty really is fundamental to us doing the right job for society.
Indeed, indeed. So, Professor, among so much geotech and very interesting projects and so many students, you have had students from all around the world.
We've had wonderful students at the University of Alberta.
I'm sure. Alberta it's a strong school in geotechnical engineering.
Yes.
It's a classical school of geotechnical engineering.
Yeah.
So, with so much geotech around, is there any hobby or leisure activity that you like to practice when you travel, maybe?
Well, I was more athletic than I am these days. I've always skied and played tennis and hiked and so.
You like skiing?
Yeah,
I see.
I just gave it up a few years ago. I have some back issues now, but all of our children and grandchildren ski aggressively and various. That's always been skiing and hiking in mountains have always been a part of my life. In fact,
Skiing aggressively.
I remember in the summer of 58, I actually thought I might become a glaciologist. I spent a summer on doing glaciology in Norway, making ice movement measurements, and thought if I could make a living being a glaciologist, I might have gone into that, but that wasn't in a clear way forward for me. So
I see.
Came back to soil.
But that's how you got into permafrost.
Well, it made me familiar with cold regions, and of course, I was always interested in frozen ground from a glaciology perspective and so on. And when I came back to Canada, and I came at the time that the need to do engineering in the Arctic exploded, so I was happily placed to be able to participate in that in the early 70s as we began to do all sorts of things in support of oil and gas industry.
I see. Very nice, very nice. And what is your favorite ski spot?
My favorite ski spot these days is about a half hour from my house here. We have 3 wonderful mountains here in Alberta, and they're just beautiful mountains, and they're great to ski. But I've skied. Actually, I skied in Santiago, and I skied in.
Oh, really?
Skied in Switzerland and skied in Austria and so on in the United States. But I live in a place that is very famous around Banff, a lovely skill that people come from all over to ski there. And that's my favorite.
I see. So how many times have you been to Chile?
Oh,
do you remember a project that you came particularly, maybe?
Well, I used to work, I think, with a lot with Luis Valenzuela. I don't know if he's on the call, but I worked in Los Bronches and other the mines just outside of Santiago, and then I worked on some of the tailings dams from in central Chile and up into the Atacama and so on. So I haven't been for some number of years, but I used to come to Chile very often with very fond memories all the time.
Very nice, very nice. It would be great to have you in person here also again.
Well, this is
very nice.
close as I'll get for the time being.
Professor, thank you very much for sharing so many details about your professional life and also now a little bit of your hobbies that you
It's
like. I mean,
pleasure.
thank you very much for sharing all of that. What do you think if we start
By all means,
with your presentation? I will share the screen. I will start sharing the screen so we can start. I will be, if it's okay with you, I will be controlling the slides.
yeah,
Okay.
yes, by all means.
All right, Professor. I think we're here. What do you see, Professor? No, maybe not.
I
That's
can
not
see
the one.
no,
Maybe is this one here.
that's fine. I
Yeah.
can see the full slides and I can see our picture a little bit on the right side, which is fine.
Ah, okay. Then it's the other one. Right.
No, it's gone.
That's number one. Give me 1 second, please. Let me double check that. I think it's this one. We should be good now.
That's good. Thank you.
No? This is the one. It's good?
That's good. Yes,
All right, Professor. Let's start. I will turn off my screen, okay?
Okay.
For you to have the full stage. Thank you again for being with us here at the University of Chile, Professor Morgenstern. Really, it's a honor for us to have you here. So thank you very much.
Thank you so much. The title of this lecture had its antecedents about actually a year before, in 2023, when the company called Rock Science, who's well known to make very good software for geotechnical world, had a meeting in Toronto in which they gave me a little award, which I was very delighted to receive and flattered, and I provided a presentation. It had the title From Certainty to Uncertainty in 63 Years. That was a year ago, and I've added on to that presentation, and it's been a year since that, and hence From Certainty to Uncertainty in 64 Years, with the timing starting when I joined Imperial College after more or less completing my PhD in the year 1960, and began my academic career, and coupling the academic career with a consulting career, which the two together provided the opportunity to gather the experience that I tried to synthesize in this presentation. If we go to the next slide, please. The work of a young academic is to transmit the things that he has done. I think you've heard in discussions that I was at Imperial College, and that was a center of discovery and innovation in the early 60s, really driving the developments in the subject. Bishop had finished his stability analysis. My own work followed on from that. It's the early days of learning how to use computers. Imperial College was doing wonderful work in the laboratory measuring pore pressures, and it was the beginning of the transference of the concept of effective stress into more and more practice-related issues of stability and settlement and so on. So you begin your career trying to transmit the things that you know, and the things that you know are dictated standards of procedures and so on. And that constituted the period of my life in which I was certain, because that's what I'd been taught in school, and my job was to transfer that certainty into the educational program, and our program was strong with graduate students in Imperial College into the practice that they're heading into. So as I matured a little bit, I began to get more practical experience assisting my seniors with some of their consulting work, and some of it began to come a little bit to my way. And out of that became the opportunity to learn the limitations of the things that I was teaching and the things that I was applying in practice as well. And one important turning point, which is the beginning of the stories that will populate the presentations, was this fairly modest dam being built to store a fly ash from the waste deposit that comes from burning coal to produce power. And it would come to this repository by train and be dumped out of the trains and stored behind, pumped out and stored behind this dam, which is this structure, which is actually a dam to store fly ash waste. And it's a simple structure. It's being constructed with an upstream portion that was a hard clay shale material. I call actually the Oxford clay, as it's called. And around this brick pit was weathered clay that was not adequate for making bricks. It had been deposited as waste and softened. And the economics of building this structure required using this soft clay as the downstream portion of the structure. The analysis was fairly straightforward. The clay shale was strong and formed the slope happily. And the soft clay was a saturated clay, and I designed that using a vein test. It was early days using the vein in the United Kingdom, but followed the procedures and used a factor of safety. I think the requirements would have been 1.5, but I think I used 1.8 in designing the slope, and it was built accordingly. One day after the structure had been completed, the telephone rang, and the owner of the facility said, "Your dam has failed." So I went out to the site, and indeed, it looked rather like that cartoon. It had slumped, it had separated between the stiff and soft clay fail, and I had at least the wit to say, well, no, it hasn't failed, it's yielded. However, of course, he was right that had water got into the cracks involved, the separation areas, there are other cracks involved, it wouldn't have been surfaceable and would have basically had constitute a failure in that regard. Fortunately, earthworks were relatively cheap, and it was easy to flatten the slope and make it function as it was intended to do. But I learned something terribly important, that the factor of safety, using design criteria common in practice, using well-established techniques for undrained analyses of the saturated soil, even somewhat on the conservative side, was not adequate to control the deformations associated with this structure, because deformations, as we clearly understand, wouldn't have been part of the kind of analysis that I had used. Had I known about the fact that the failure when the vein would be many more percent strain that would be common because of its ductility, I might have had the wit to use a factor of safety of 6 or 8 or 10 or something like that to control deformations. But that was my first encounter of uncertainty in that regard. And the case histories that the flow grew out of that as I became increasingly exposed, mainly in the consulting, the practical world, whether they were practical projects of research or related consulting activities, where you encounter more uncertainty than you will in the classroom, of course. We go on to the next slide, please. There are 3 sources of uncertainty which are well understood in the vocabulary of uncertainty. There's parameter uncertainty related to the variability, let's say, of the shear strength spatially and how to do the tests. There's model uncertainty, the uncertainty that I just talked about. Just go back. Model uncertainty that I just gave a little example of that with the stability analyses that wasn't fit for purpose and not having deformations embedded in it. We have many examples of model uncertainty. And there is human uncertainty, which is going to be a large portion of the learnings that I'll be presenting to you. Next slide, please. In 1990, could you go back to, yes, I'm sorry, is that slide 3? Yes, in 1990, I was asked to give the first Lum lecture in Hong Kong, named after Peter Lum, who was the first to go to Hong Kong and teach modern soil mechanics and developed, just go back, please. Go back one. So no, the next one, please. there. And this lecture was is an honor. He had passed away by this time. And what I wanted to do to understand how good were we in prediction as a beginning portion of that lecture. So I was going to look at case histories, and I set up this classification that if a prediction, a stability prediction or a settlement prediction was within 5% of what actually happened, then that would be excellent. If it was plus or minus 50%, that would be poor, and so on. And that was the classification that I used and applied it to a number of case histories. Next slide, please. Go back. The case history that there are a number of case histories in this LUM lecture, and one that is particularly striking is the case of the Mauer embankment. The Mauer embankment was an embankment being built on soft soil in Malaysia. They're beginning to expand extensive development of their highway system, and they thought they would build an embankment to fail in order to refine the analyses. And they had vein tests and undisturbed sampling and all sorts of good things in order to populate the test. And people would then submit their prediction of the failure, and that was the outcome of the prediction competition. They had 31 predictors, and I summarized using the classification I told you about how good they were. And you can see that of the large number of predictors, there was only one that was excellent, and many that were poor, and a number in between, for a relatively simple problem of building an embankment on soft soils. But when you imagine the methodology at the time, and even today, you had the vein test, you had undisturbed samples, you had sensitivity, you had rate effects in interpreting the vein, and all of these matters that cloud the accuracy of which accuracy of the prediction, and all of them embed various degrees of uncertainty, which prevailed among this group of very good predictors, of very well qualified predictors. And the LUM lecture has a number of examples like that led me to the conclusion that we're not very good at prediction. This is summarized in the next slide. The next slide.
Professor, can you give us, please, 30 seconds to double check something that might be happening with the screen?
I can't proceed without it.
just to double check that everything is working well. I will share the screen, and now I will share the screen, and I will initiate again your screen, Professor.
Okay.
Thank you very much. That should work better now.
So we go to the next slide, please. As I was pulling together these case histories in the LUM lecture, I came across this wonderful statement from a gentleman called Southwood, who is an environmental expert and was dealing with the uncertainty in environmental matters. And I thought it appropriate to capture that. And it said, the things that we'd like to know may be unknowable. And I thought that certainly captured the situation for me in 1990, and you'll see as we proceed further on, aggravated even more with more experience. There's an intrinsic uncertainty in our business. If we could go on, please. Next slide. The next case history I want to draw to your attention that explains uncertainty, and I'm drawing it mainly from my own experiences as opposed to issues of others. We'll talk about the widespread aspects of uncertainty, but this is the city that I lived in at some time, and you can, if you look down, you'll see a bridge in the middle, and to the right of the bridge was a location in which a large convention center was to be built, and a building down on the slope. and we were involved, this is now, I guess, the 1980s and so on, in evaluating the location for building this convention center. So we have the next slide, please. This is the geology in that valley, and it was well known to be, we have in the city of Edmonton, a Cretaceous clay shale with zones of bentonite and a well-established history in the river valley. And you can see that the intent was to build over this landslide terrain, draping down into the valley. And you can see the movements, you can see zones of weakness declared, you can see layers of bentonite within the sequence, which we'll speak about, and overriding that, Pleistocene deposits, tills, and later alluvial deposits. And after declaring what the geology was like, we said you can't build over that location. But if you can fit into the portion of the valley wall that has not undertaken a landslide, we think that you could house this large convention center within that zone, and that is to the left of the slide. So the architects began to reconfigure the design of the convention center, which of course, being located to less extensive real estate, had to go deeper into the ground than they might have originally intended. And that was the problem, was to develop a deep excavation to house this convention center in the material that had not participated in the slide, but as you can see, the geology is disposed to instability. Next slide, please. So studies were undertaken. I was involved as a review consultant, and we obtained samples of the in situ material using best available technology at the time, triple true coring. And we have this material that is a Cretaceous clay shale, the Edmonton Formation that you see in the dark core, and embedded within it, you see that light band, which is a zone of bentonite, which I logged myself, because the bentonite is known to be on the weak side. But more particularly, we have a situation where you have glacial deposits on top of weak foundation rocks, which can produce glacial drag that can create conditions of residual strength in these deposits, which means that only the residuals, due to the slip, due to the glacial drag, only residual strength should be operated. So these things are logged, have been logged for a long time in great care, to looking for slickensides. And I logged that bit of bentonite myself and found it intact, logged it carefully, and concluded that we could proceed in the design using the peak strength of the bentonite as opposed to residual. The peak itself is not huge, it's 14 to 15 degrees, but the residual might be as low as 7 or 8 degrees. So the design proceeded accordingly, which you can look at the next slide. And this is what was ultimately built, a tangent pile wall with permanent tiebacks to create the space in which this facility is going to be housed. At the time, the permanent tiebacks were among the highest load tiebacks constructed, because the conditions required to build the wall was to make the deformations associated with excavation nominally zero, designed against K0 pressures, because there were adjacent structures to the left on the slide in which any significant movement would result in cracking and so on. So that was the design of the retaining systems, and you can see it proceeding. And if we go to the next slide. So that is the design. You can see the different rows of the tiebacks. You can see the presence of shear zones, in which were taken into account some of the residual stability analysis figures. You can see the stress distribution that was applied, that the tiebacks had to honor in order to minimize the deformations at the wall. And you can see that the bentonite zone that I drew your attention to at elevation 635 is also a potential failure mechanism, in this case with peak strength, based on the characterization of the core that I logged. And we then, as obviously was instrumented, we had inclinometers and so on. And as we began to excavate, if we look at the next slide, you'll see what we saw. So as we began to excavate, and we certainly weren't down to full excavation, the lower shear zone, which is the bentonite zone, began to slip. And we excavate a little more, and we'd slip a little more, excavate a little more, slip a little more, and obviously progressive failure was occurring at depth below the excavation because of the lateral unloading effects at that depth. It was a very uncomfortable situation to come in the morning and call this project off and say, they'd excavate a little bit. Did it slip a little bit? Yes, it slipped a little bit. And that was something that we began to live with. And it was, fortunately, we had a fairly large factor of safety against deep-seated sliding of around 1.8, and one could accommodate a reduction in strength. Had it been to 1.5 or something like that, I might have had to retire and live in Chile, which would have been a pleasant thing to do, but it was certainly a very stressful condition. We did not have an understanding of analyses of that material. We didn't have an adequate way of characterizing the progressive failure to develop. This is 1978, 1980. Later on, my then subsequent student and then colleague David Chan took on the finite element analyses of this with progressive failure and strain weakening, and actually began to simulate effectively. You can see some comparisons with the finite element calculations, which are not perfect, but certainly encountered for the major effect being done, shall I say, now 40 odd years ago. But we couldn't do that at design. I was conscious of the potential for shear in that bentonite. We could do elastic analyses properly, and we did an anisotropic elastic analysis reflecting that the resistance in the horizontal direction would be less than the vertical. And if we calculated stresses that would violate the shear strength, we would then put in a lower strength, but we never did. So the anisotropic elastic analyses never forecast the kind of phenomenon that we saw, and that was part of the growing understanding of uncertainty associated with this project. Carry on, please. Thank you. An important learning curve. The Lum lecture that I referenced has a number of other examples, some from my practice, some from other practices that dealt with the inaccuracies, the uncertainty, perhaps sometimes the errors, but I'm not speaking to voluntary errors, involuntary judgments involved in our practice. And I concluded from that lecture that the assurance of geotechnical performance would be enhanced if geotechnical engineering shifted from the province of certainty to the analysis of uncertainty. And in a sense, this lecture is the summation of my focus on uncertainty that has been very much in the front of my mind and evaluation and of both research issues and, more importantly, practical projects that I've worked on. Can we go to the next slide, please? Now, I'm not alone in understanding uncertainty. I mentioned that I gave the first form of this lecture at a rock science meeting about a year ago, and John Curran and Dr. Hama are some of the senior people in the rock science company, and I was very pleased to come across their comment in this paper that I've referenced. Could you go back, please? If room is therefore not made in geomechanics software analysis to accommodate uncertainty, any conclusions will be open to question. So that certainly resonated with the concerns that I have been summarizing for you. But my response to that is certainly uncertainty needs to be addressed, and we'll see another issue, another reference in the next slide, please. The next slide that I found in preparing for this paper and its predecessors is this, and it was by Professor Foon and his group on the ISSMGE Technical Committee 103. And this is a very powerful group of people, very informed. The paper Geotechnical Uncertainty Modeling and Decision Making, published in the Japanese journal Salza Foundation. Excellent paper. And it says geotechnical software can provide better decision support by computing the probability of failure, reliability in clay as one basic output in addition to stresses, strains, forces, and displacements. They conclude the purpose of numerical modeling is to enhance decision-making in practice rather than enhance our prediction ability. While these are certainly people who understand the issue of uncertainty, I don't agree with their conclusion, as the rest of this presentation will argue. There is certainly understanding, and most of these predecessors, Mr. Curran, Dr. Curran, and Professor Foon all thought that the best way of dealing with uncertainty is to develop probabilities of failure, and we'll see that my experience with that is not so positive, though my experience with the other ways of managing uncertainty is much more positive, which is the ultimate theme of the lecture. Next slide, please. I've had a lot of opportunity to learn from being involved in the Syncrude tailing span we have in Alberta, where I live, a large industry called the Alberta oil sands industry, which involves very substantial mining and processing and tailings production to develop bitumen, which is then upgraded to crude oil. And it produces huge tailings and fascinating mining problems and so on. This was at one time, maybe it still is, perhaps the largest in terms of volume tailings facility in the world. It's now basically finished, but there's always been a source of much learning in working with that over the years. This is in plan. You can see that it's very, I can't remember how many kilometers long it is, perhaps 15, 20 kilometers all around. And therefore you can't do borings every 100 meters. You had to pace out your spacing of the investigations and proceed observationally to then concentrate on worse conditions. And you'll see on the right side, cell 23, which became an area of major concentration because it provided the most extensive weaknesses as we began to build this facility. Next slide, please. Now, the geology at this location is Pleistocene deposits, glacial deposits, and so on, overlying a Cretaceous clay shale of high plasticity. And when you do that, you create glacial drag, which I've spoken passingly before, but here's a picture of it. So this material has been sheared, not because it's a landslide, it's been sheared by glacial action. And sometimes these rafts of this weak material can be embedded in the till, but also the interface between the till and the bedrock also has zones of low shearing resistance because of the called glacial tectonic action creating shears. So this is an indication of the kind of defect that plagues us here, and you'll see plagues us in a number of other locations in the world. Next slide, please. So as the dam began to be built at that cell 23, which is the zone of the greatest weakness, and we saw an example of the greatest weakness, and you can see that it's manifesting itself down at the interaction between the till and the bedrock, if you will, part of it rafted material, and you can see the deformations as we build more. Deformations are developed, measured by the inclinometers that are monitoring this, and build a little more, get a little more deformation. You can follow the history of the slope. You can see it started at one slope, was flattened, and continued to be flattened, and so forth. So that has a learning, if you like, from the observational method. And now we're going to see whether we can how we can manage some of these things, if we can, by probabilistic methods, and then if not, by other, which we'll see are superior methods. Next slide, please. This is the situation at that location. You can see the failure mechanism going into limit analysis. You can see you have a breakout zone, a passive zone that has to go above the till into a sandier till, providing passive resistance. You have an active zone that is pushing down through the deposits, and you have the resistance being developed at the disturbed clay shale zone with the history that we've just looked at. And we're going to explore this. We're going to explore some other cases, whether we can proceed to analyze probability of failure in this case. Next slide, please. If we're the original designers doing the investigation over this structure, and we wanted to say, I know the stratigraphy, I get that from the boring, and I can sample it, and I'm going to sample over this large area that we talked about, what resistance would I indicate in the early design stage? And this from well-qualified consultants who knew about what to look for, but were making measurements in a variety of locations, would give you some degree of the dispersion of resistance that you had to get at, as opposed to the 7.5 red line, which doesn't reflect a dispersion, but it can be obtained because we now monitored and found out where it is. But this would be the kind of, if you're doing a design and you're looking at variability, the kind of variation you'd have to be thinking about managing to calculate a factor of safety. If you go to the next slide. We have pore pressures as well, and these are the pore pressure variations at locations away from the toe, and you can see that at a given section away from the toe, there's a significant variation of the pore pressure itself. So there's another variation of input that would go into the stability analyses. So we began to ask ourselves the question. It would have been about the year 2000. What is the probability of failure of a safe structure? And we had case histories like this one. We had other case histories that were in the literature in which you could say it failed. We knew the factor says one from failure. You could then reanalyze the slope or the dam and make it safe by a reduced strength, but you still have the dispersion of the input data, and you could calculate the probability of failure of what a safe structure would be. Could we have the next slide, please? And when we did all of those things, so these are failure cases, which are the black squares, which there are a number, and the round circles were cases in which we developed very elaborate probabilistic analyses with the dispersion of data and so forth to calculate the probability of failure of a safe structure. And you could use the reliability index as one measure of the probability, or probability of failure itself as another, which I haven't plotted here. And this is in a thesis published at the University of Valdor about 20 years ago. And you can see that there is little, if you ask a structural engineer who's happy to do structural probabilistic analyses, what's the appropriate reliability index to design, you'd get an answer in the world of 3.5 to 4. There's only one case history which has got a much higher reliability index, which would say this is very, very little probability of failure. And it's the Lodalen landslide that occurred in Sweden, a very uniform slide, which rather limited data to actually explore the variability of the strength, which accounts for the fact that the probabilistic analysis of that case history would give you comfort, but you wouldn't get a lot of comfort in trying to create a probabilistic index criterion for failure to replace the factor of safety from all of our other case histories, which range from soft clays, the Mauer embankment that I talked about, other slopes, and residual soils, and so on. So we actually took the view that well, first of all, the structural engineer would say, look, a reliability index of 2 is too low, your probability of failure is too high. And that wouldn't be news to us in geotechnical engineering, knowing that we do take higher risk in our work than some of our colleagues elsewhere. And that, in a sense, is reflected in that data, but that's our data, and one wouldn't have thought that factors of safety 1.4 or 1.5 would have been excessive in our world with the other ways that we have for managing safety. So we actually abandoned some 20 odd years ago the pursuit of probabilistic based failure, because we didn't think from our case history studies, as opposed to theory from our case history studies, that we would find something that changes the way we do business. The next slide, however, said there are ways in which we will find a means to change our business. And this goes back to our early experience between deformation analysis and field measurements for the very same case that we're looking at. We had inclinometers in the passive zone of that facility, and you can see a comparison between field measurements and finite element simulation of the field measurements. And this is going back, what are we talking, 30 to almost 30, well, 14 and 30, 34 or so odd years ago, in which we're getting, this is a research, this is not practical, this isn't being applied, though it gave us comfort in this particular case, but it was a research study that said, hey, look, we can actually get a good fit between what we're monitoring and what it is we're computing, even with the technology of those days, which of course were challenging because this was work at a PhD level. Next slide, please. However, from that kind of work being conducted, as we see 30 years ago, it led us to the view that for the class of potential failure modes exhibited by the synchro tailings dike, which we just talked about, it is both possible and effective to construct a numerical model using a history matching approach, and this provides insight for the evaluation of both past and future performance. This became the seed of much of the work that's guided my thinking, because it's the seed of what we now call performance-based design. So the way forward that is positive, if probabilistic analysis is not positive, the way to manage the uncertainty is, of course, to embrace it in a history matching, computationally based numerical analysis of what's going on. Let's go on to the next slide. I also, the next slide after that, I also concluded in a paper, a review paper on stability in ASE some years ago, one can imagine a time when simulation is so firmly embedded within the observational method that it becomes recognized as an essential tool in assisting the practicing engineer to evaluate correctly all of the information available to him. This places a greater burden on the engineer to recognize and understanding in an ongoing manner the limitations of advanced analysis. This, if you like, is another early learning about the potential and the challenge of doing performance-based design. Next slide, please. A major advance in our optimism that this is the right way forward came with the case study of the Alameda Dam, which is shown here. The Alameda Dam is a flood control structure in southeastern Saskatchewan, based to control flooding coming down from the rainy terrain that it controls and going into cities and across the border in North Dakota, United States. You can see the main dam, and you can see the spillway and the low-level outlet for the drainage system on the right-hand side. We go to the next slide. In the year 2011, the dam was completed. I'll talk about some issues during construction, but when it was completed in 2011, the reservoir surcharged about 5 to 6 meters above full supply level, near the maximum of allowable flood level, in order to manage floods that were coming down. It was doing its job as required. However, that loading, the dam had been happily sitting there, that loading increased rates of shear displacement in the clay in the foundation. Consultants were retained who came out and did a stability analysis for lookabout and said that there is a factor of safety that they calculated using accepted techniques, and therefore you have a very serious problem with this dam. The recommendations were to lower the reservoir as soon as possible, carry out site investigations as soon as possible, conduct detailed assessment, and so on, because of this concern that it was sitting imminently ready to fail, and with certainly an unacceptable degree of factor of safety for a dam holding a lot of water. Next slide, please. The background of the dam is it's not a very high dam. It's 42 meters high. You can the slopes are fairly routine, 3-to-1, upstream and downstream. But the downstream is supported by a very extensive berm. The dam, notwithstanding a knowledgeable review board and experienced designers, actually can develop very substantial deformations in its foundation during construction. And I was retained to review at that time, the reason for the imminent failure during construction was the fact that the stratigraphy was till over another clay shale with a weak residual at the interface. So the kind of mechanism we saw at the Syncrude tailings dam was also here at this structure, and that had been ignored in the design, and it was moving, and we stopped construction for a year or so and had to build very substantial berms that you see downstream. But this is the structure that moved under this flood, when that's the history that it did have a weak layer in the foundation, but by this time well known and under control until the flood came along. Next slide, please. The drainage of the dam, as you see, is fairly routine. A chimney drain going out to a blanket drain with an extension that you saw that would be emit the drainage. The dam, from its history, has lots of pulsometers, has inclinometers, and so on, providing a basis for the consultants who assess the danger of the structure to be confident they had decent data. Next slide, please. So the account of the structure I've just described, there were high pore pressures developing during the stratigraphy. There were movements developing in the clay shale due to the weakness, and I indicated that we had to stop construction for 18 months while we amended the design, and finally completed in 1990, and was happily performing until that storm some 10 years later came along and triggered the concern. Next slide, please. Here you can see the high excess pore pressures related to construction. You can see pore pressures well above reservoir level, and you can see rather slow decay, which is not uncommon in these high plasticity materials, very slow construction pore pressure. And you can also see that there is some response to the dam in terms of reservoir fluctuations. If they go up a little bit, you get some changes in the response of the structure. Next slide, please. The foundation movements are well characterized. Here is the data from the inclinometers that you can see giving clear indication of slip surface and very substantial movements that occurred during construction and which moved again during the flood condition. So the mechanisms are unambiguous as to what happened. Next slide, please. Now, the analyses, if we're looking at the lower left-hand figure, we see the dam, we see the spillway, we can see the outlet channel. The analysis that the consultants had undertaken were limit equilibrium analyses, two-dimensional limit equilibrium analysis, going from the dam into the basin at the outlet, into the basin at the spillway. The spillway decanted into a basin, so that there was an excavation in that basin, and the two-dimensional analysis that gave a factor of safety 2 was in that direction. A factor of safety unit is in that direction. We replicated that number, and the arithmetic was correct. However, we thought that this is a situation in which one can have some reliance on three-dimensional analyses. So we undertook three-dimensional limit equilibrium analyses. Now, you might remember the cross-section has this weak layer at some depth, but clearly the side shear resistance going down to that depth in the analysis is significant. So this is a circumstance in which I and others have become accustomed to utilize three-dimensional analyses in support of stability. And we did that in this case as well. Perhaps this is one of the cases that began to give us more confidence to do that. And you can see that the minimum factor of safety by three-dimensional limit equilibrium analyses, whether it was in the conventional direction, normal to the dam, or in the inclined direction, gave us higher factors of safety than unity, and the minimum being 2 due to three-dimensional effects, which gave us some confidence. Next slide, please. And the owner wanted to know, well, look, I've got this defect. It's troubled me up to now. What's going to happen for the life of this structure? And we thought the only way to determine what it's going to be like for the life of the structure, now that we've set aside the issue of emergency, is to develop a three-dimensional deformation analysis. In this case, we use FLAC to simulate what had happened, and then to use that model to forecast what might be the behavior of this dam for its service life. So you'll see in the lower left side the results of the inclinometer data together with the FLAC analyses within the shear zone, and you can see the vectors in the upper left side, and so on. And in the lower right-hand side of the conclusions, that we got a pretty good match to the shear displacement magnitudes that had been monitored, but the matching displacements and direction was not as successful. We didn't get some anisotropy that's in the whole mechanism adequately, but we didn't think that was a fatal flaw. In fact, we regarded this facility to have a fairly good field equivalence of behavior. It's a phrase that I use continually now for deformation analysis. What is the field equivalence? Is it adequate? Are we matching the important things correctly? And this was adequate to then project what would happen with cyclic fluctuations of reservoir for the next decades or so forward, and provide some comfort that the structure is going to behave as intended and it's in service today. But from our perspective, we were now linking performance history and then performance projection using deformation modeling with a reasonable consistency with the limit equilibrium. We're not throwing that out in any of our work. So the Antamina case history, which has been published, the references there, was an important confidence building case history for moving forward for the linkage of relying on deformation analyses with a high degree of appropriate level of accuracy, appropriate degree of performance matching as for making engineering judgments. Next slide, please. So having matched the model response to economic data, we just indicated that we could generate reasonable fit, and that was all important findings. However, we learned something else. We learned that there are different ways of this mechanism which could go to failure. when we try to decide if we're going to continue to have cyclic loading on this, what is its resistance in the long term under the mechanism. If you look at the definition of the factor of safety, it's that number by which you reduce the strength properties to bring the mechanism into limit equilibrium. It is actually a kind of loading path, conventional strength reduction, consistent with the definition of limit equilibrium, gives you the loading path to failure. You're going to reduce the C and the phi in that three-dimensional mechanism to different values. However, if you go back to the cross section, which we'll see in a moment, it wasn't being held up by the horizontal material. It was already fully failed. You couldn't actually reduce it anymore. It was all being held up by the till in the passive breakout zone. And therefore, the failure mode should focus on reducing the strength of the till until failure occurs, which gives you a different number in terms of what its ultimate resistance would be. I think this is illustrated in the next slide. And there you see the case history in which one is reducing the, in which one was evaluating the factor of safety to bring it into failure. And the left-hand side is the traditional factor of safety, and we're going out to very large displacements at a factor of safety, whatever that number is. I think it's 2.2 or 2.24 or something. No, 1 point. Well, I'm sorry. Reducing the strength to 3.6 would bring it out to a factor safety unity for that mechanism. However, if you say, I'm not going to reduce the strength along that because it's already at failure, it's being held up by the passive zone, and you reduce the resistance in the passive zone until it fails, you'll find that the resistance at which it takes off is 1,500 millimeters as opposed to 3,500 or 4,000 millimeters, and therefore illustrate if you get into the prediction into the factor of safety numbers themselves, but clearly the mechanism of till-only strength reduction is a more critical mechanism than the conventional factor of safety. So our exploration of the linkage between deformation analyses and the granularity that it provides with factors of safety considerations was revealing in this regard. And I've been meaning to develop a better vocabulary for these different mechanisms, but basically I hope you understand that the factor of safety should have a different name when you're applying it only to one element of the supporting discipline. I'll come up with names sometime. Next slide, please. So this case history gave us a significant amount of confidence in the methodologies that we're now going to be relying on in more detail in the rest of, and extolling in the rest of this lecture. And as I discussed in a summary paper that I also gave in Hong Kong on a special occasion not so many years ago. But looking to the future, we can move from what I now call precautionary-based design, which is our standard practice. We calculate factors of safety, we monitor, we have the observational method. We're still making observations, but the observational method are not paying attention to the detailed pore pressures or the detailed deformations that we're monitoring. It's making sure that we don't have a mechanism that's catching us by surprise, that we have ignored in our design methodology. That's why I call this precautionary based. And we can move to performance based design, in which we have all of the reserve resistances, all of the monitoring, the observational method, and we have real-time responses, and we can recalibrate all of these inputs incrementally in a kind of Bayesian updating way to ensure that we're always catching the right history of the past and have greater reliability making the forecast. And that is the basis going to be the remaining part of what I'm going to be emphasizing for you. So these ideas were coming together some 5 or 6 years ago. Next slide, please. a lot of the opportunity to bring the substance of the remaining part of this lecture came together when I was invited to give the sixth Victor de Mello lecture, and I used the title Geotechnical Risk Regulation and Public Policy, and it's available on the Victor de Mello website, both the visual aspects of that lecture, which I'm going to take some portions out of, as well as the published version, which was published in the journal Soils and Rocks, which I think is their journal. So if you want, so the focus now goes into geotechnical risk and its implications in public policy. Next lecture, please. Next slide, please. And we're going to be talking now, we're going to be moving into the world of tailings dams. It's been so catastrophic, which is so important to many of you in Chile, and repairing the things that have happened there. But I want to begin with the work that when Victor de Mello and I were involved, and some others, in Hong Kong in 1977, or about 1977. Up to that time, Hong Kong was having an explosive immigration of people coming from mainland China, living on the street virtually because there was nowhere else to live. A huge expansion of housing and apartment buildings and so forth to house all of these people. And a lot of failures were taking place. You can see the kind of fatalities that were occurring. The Poshan wrong one in particular created 150 deaths when that building collapsed. And it was part of their business practice. And the Sao Mau Ping failure in 1976 that created some, I think, 24 deaths or about that, created a situation in which the governor in Hong Kong just thought we had to do things. They had to do things to change the way they were doing business, and they invited a group of specialists, Victor and myself, and others were invited to come and give them advice, which we did. And I won't go into the detail, but we did recommend that they change their engineering practice from what had been an old colonial public works practice with little geotechnical knowledge to one that had its own mandate to deal with geotechnical engineering, because you needed to change things quickly and they need to be empowered to do that. And that was accepted by the government, and began the development of the Geotechnical Control Office, it was called at one time, or the Geotechnical Engineering Office, as it was controlled subsequently. And you can see that the implications of that change was very rewarding for all of us, because the data that 15-year average rolling of fatalities indicated the time in which all of the activities of the GEO in Hong Kong created a community that deserved, that had a safety from geotechnical hazards commensurate with their well-being. They could do these things. This wasn't an undeveloped part of the world if they knew what to do and they learned how to do it. But the important point I want to make here is certainly there were analyses and site investigations and so on, but the next slide indicates what the secret of safety was. The secret of safety, and this is to be generalized when we talk about tailings dams in particular and other things that we're all responsible for, comes not from a single calculation, not comes from a single monitoring, but comes from a safety system. And that's what was created in Hong Kong, that involved understanding the slopes and checking and understanding the geology and quantifying risk and landslide warnings and all of this totality of this system that was the learning for most of us as we all participated in assisting Hong Kong to achieve their wonderful end product. And when one is involved, as we're now turning to matters of safety in dams in particular, you could apply it to tunnels as well. But what is the safety system that we're exploring, that we're evaluating? And it begins with a safety culture. What is the community or the company? What is the safety culture that creates the situation to engage in this diverse number of activities that have to be accumulated and applied and reviewed, checked, and so forth in the safety system? Next slide, please. So we're heading toward, as the Danilo lecture did, heading toward the world of tailings dams, but I want to go through the world of water dams before we get there, to indicate that safety can be elusive unless you're all inclusive. I didn't mean to make a little rhyme, but that's it. This is the Oroville Dam in California, and you can see that the spillway has been eroded, and it was in the I can't remember exactly what year, but some years ago, not too long ago, but some years ago, there was a flood coming up in this part of California. The Oroville Dam is owned and managed by the Water Resources Department of the state of California and the Bureau of Reclamation. One of the terms of containment, one of the largest dams, if not the largest in the United States, and it's received nothing but excellent attention. Thank you, Juan Gray. 10 years ago, this occurred. And there was a plan to control this flood by utilizing the spillway, and they found when they did that, the spillway wasn't functioning as intended, and they ultimately had to. There was no other safe way to manage the potential of the flood. It was still raining, and they had to evacuate downstream almost 200,000 people because of the potential of losing the dam in the event that the rains continued. Fortunately, they didn't, and no particular later outcome arose from public safety point of view. But the question, as was well studied by John France and an excellent group of consultants, how can this happen in a situation that has been such review and inspection over the decades, satisfying the high culture of the two dominant organizations. I happen to know a colleague who was chairing a risk analysis on this prior to all of this happening, and they had the risk assessment of the spillway on their risk register, and the view was, well, this was a risk related to failure of the dam. The view was, well, we needn't keep that on our risk register because the dam is on bedrock, and therefore it will function as intended, and therefore it was removed from that particular risk assessment. And we can see that the pervasive fault was deeply embedded, not only in the physical aspects, but also the psychology of doing risk in this case. Clearly, the foundation was not built as intended, and all of that is a learning curve. That some of the things that we're going to be talking about maintaining the integrity of the safety culture requires continuing review and checking. Next slide, please. Now, I've been involved over the last, I guess, virtually decade now, in a number of significant tailings dam failures. And this is the Mount Polley tailings dam failure that occurred in British Columbia, 2014. You can see the dam in the upper left. It's been eroded out by the flow of tailings. You can see the flow of tailings flowing here, and they went out to the right of the slide out into a stream and a lake. Fortunately, people were camping there. Nobody's there. There weren't any casualties. But we're talking of a structure built by knowledgeable engineers and design. We're talking of an owner that wasn't one of the largest mining companies in the world. It was a substantial company that certainly was I think not trying to reduce budgets in any significant way. And we're talking of a constituency, the province of British Columbia, that has a very deep mining culture and the regulatory system and so on. And yet this troubling event could occur. Next slide, please. This is one that you also know. This is the Samarco failure. I chaired the failure assessment on this as well. And you can see the failure on the right-hand side. Part of the structure is still intact on the left-hand side. Joint venture of two of the largest mining companies in the world, Vale and BHP. In Brazil, also with a well-known mining industry, also with a review process. One can argue whether it was extensive as a BC one, but certainly we're not dealing with companies that are struggling with understanding the industrial culture that we all work in. And go to the next one. This is the Cadia failure in Australia. As I was writing the Brazil lecture, this occurred. The sad irony. This is Cadia Dam in Australia in New South Wales, owned at the time by Newcrest, one of the largest mining companies, and now part of Newmont. In New South Wales, it has the longest and deepest tradition of risk analysis of dam safety. Again, there is no lack of desire to cheap budgets or things like that with controlling. So this was troubling again, like the others, that these are issues occurring by people in environments that we've all assumed would know much better than to tolerate them or doing. Certainly they're not tolerable, would know to house them or have them occur. Next slide, please. Now, after the response of those dams, the International Council of Mining and Metals took some role. And for those of you who may not know that, the International Council on Mining and Metals is the association of the largest mining companies in the world. It represents the industry. Now, it represents the industry both to ensure that the industry, clearly it's influential, but it's not a crude lobbying group. It also sets policy and standards, and all of the largest mining companies are part of that. So they took some actions, and they retained our good friends at Golder to do a study, review tailings management, 2016. They went and did a study. And next slide, please. And the study concluded that the review concentrated on governance issues and reflected that basically governance issues as opposed to technical details were this major issue. And basically that's what's in the text. If one were to focus on these and other case histories, consolidation, a greater number of failures, investigations resulted over the last 20 years, is there anything missing from existing standards and guidance documents that was known and could have forestalled such events? And the answer would be as below, that they're fully embrace the knowledge required to embrace such failures. So let me go on to the next slide. So ICM then produced this documentation, and documentation that comes out of ICM and recommendations that come out of ICM are generally have the full agreement of their participation, and therefore have the burdens of compliance. It's a compliance by the peer group related to what comes out of these position statements. Next slide, please. And I felt uneasy about the recommendations that came out of the position statement. The technical team that had come up with those recommendations had used 3 case histories to support their studies. One was Los Frailes, the failure in Spain. The other was a Mount Poly case that we looked at, and the other was Samarco in Brazil. And as it happened, I had been involved as reviewer of the failure of all 3. And it didn't ring true with my experience to say that technical issues were not paramount, as opposed to governance issues being the dominant feature. And I began to put together in the Develop lecture the cases related to tailings issues that I've been involved in. some significant failures, like you can see Los Frailes is there, Poli is there, Samarco is there, and some that I knew about the file because perhaps a colleague had been involved or enough had been published for me to make a judgment of the basic causes. I'm not talking about root causes in a legal sense, but what is the basic cause? And I broke it into three: one engineering, other operations, and the other regulators. The Los Frailes, we'll see presently, from my experience there, had a significant engineering problem. Poly, you'll see, has a significant engineering problem, and Samarco had a significant engineering problem coupled with some operations. There also, I don't know whether your screen has a block on top of it, but there are some cases in which the regulator has a problem. For example, the classic case of Stava that killed so many people, in my view, was primarily a regulatory issue as opposed to a technical issue, because they worked on that failure of that one in some detail, the late D'Apollonia, Elia D'Apollonia. It had been put into service after it had been closed by the major mining company and put in the hands of those that were not qualified to do that. So there are different issues filling out these things, but engineering as a basic cause was highlighted in all of this integration of my experience. Brumadino is down at the bottom, which came after this. And I later, in another summary lecture, gave at a conference a few years ago, instead of calling it engineering, I called it embedded ignorance, the kind of mistakes that I was talking about in that little dam that I was involved in some years ago, or the kind of mistakes that I made in the convention center where I didn't get progressive failure right. This is not to be offensive to anybody, but these are mistakes that we have all made in our operations out of good intent, nothing to do with just not knowing enough to do the right thing. Let's look at an example. Next slide, please. So this is the breach produced at Los Frailes in Spain. You can see the dam is gone, the tailings have flowed out. Fortunately, nobody was hurt, but it was the tailings were extremely toxic, and they flowed into a wonderful parkland, pristine area of wonderful grasses and flowers and so on, and produced possibly Spain's worst, if not worst, one of the worst environmental disasters. And ultimately, the mining company that was Boliden out of Sweden, who was mining here, had to give up the facility and retreat. This is a picture, and you'll see in the next picture some analyses that was done at the time. Next slide, please. This is the stress strain curve of the foundation of the material. Now, this is a sample we obtained in the forensic investigations, and we sent elsewhere out of Spain to do ring shear tests, collecting this strain weakening. And my past colleague Joaquin Martí in the university in Madrid was able to do this in finite element work. Sorry, I'll talk about that in the next slide. We see the strain weakening material very evident. Now, I asked the past president of Boliden at the time, how did you get there? He said, well, we came to Spain, we didn't know about tailings dams, and we asked for the best to do this, and this is what we got. So there's clearly no evidence in the design of this kind of clay behavior. There were no pore pressures in the design that would have picked up high pore pressures leading it. There were no inclinometers and so on. And these were, at the time, acknowledged as capable designs. This is the work done a long time ago. We couldn't publish all this stuff because the material was under litigation for a long time, but Professor Martí was able to get some of the papers published, and Professor Jens and others from Barcelona actually later on published a lot of the details. So this was the early stuff that we came from our forensic study indicating that the kind of failure was if you like, entirely predictable by advanced techniques at the time, but certainly the important point is that the characteristic of the foundation holding up this critical structure was not recognized in any significant way. Next slide, please. This is a case that you won't find particularly in the literature. It's not a secret, but you can see that this is a tailings dam in the province of Alberta holding up fly ash, which you can see, and it's being raised, and you can see cracks developing. Fortunately, not creating a failure. And there's a foundation here involving a soft fissured clay that has some strain weakening associated with. And these conditions were not well understood in the foundation, in the design of this mechanism, which, as I say, fortunately didn't create loss of containment of the material to the left. But the problematic kind of ground that was built on was recognizable. Another example of what I've called embedded ignorance or engineering basic cause. Next slide, please. So I wrote in the DeMello lectures, the most important finding is the dominant cause of these failures arises from deficiencies in engineering practice associated with the spectrum of activities embraced by design, construction, quality control, quality assurance, and related matters. This is a very disconcerting finding. There is an unwritten covenant in our professional practice with the assumption on the part of an operator that given reasonable resources and on the part of the regulator that given technical guidelines and a modicum of inspection, the engineering team can be relied upon to produce a tailings storage facility that perform as intended. Experience summarized here leads to the conclusion that this covenant is broken. And I then follow that by the conclusions in the ICMM-sponsored study and the recommendations embraced by the tailings governance framework issued by ICMM in 2006 were not adequate to resolve the crisis. It remained at this stage within the industry. Next slide, please. So I then took it upon myself within the DeMello lecture, which is what, 2018, to put forward the outline of the way forward, which is to begin to rely on performance-based, risk-informed, safe design, construction, operation, and closure. All of these had to be developed within the design, control, operation, closure methodology, at least for tailings dams in the mining industry, and by inference in the water industry, which is separate, different, a lot simpler than the tailings world. So stage one is conceptual. You need an operator, you need a review board, you need to do uncertainty assessment, potential problems analysis, multiple accounts analysis or decision. These are illustrations of the components that should be going into the way we do our business. The next slide, please. Stage two is feasibility, so it goes on to after you've chosen the way forward from your decision analysis number 5, then you've got to go into engineering record responsibilities, design, risk assessment, quality management. All of these are part of the safety culture, but it all has to be driven by the safety culture declared by the owner. The owner has to declare the culture and has to support, whether it's manpower, whether it's at the board of directors level, achieving the safety requirements, just as they have in work safety, they've got to have it in dam safety. Next slide, please. Construction, I think we go on to the next slide. Closure is also there. I'm not sure we have a slide for closure. Yes, so all stages have to be embraced by the process of safety management in this more comprehensive manner. It's not just a factor of safety. Next slide, please. So at that time, I had made a recommendation to the ICMM that they should change what they had published and pursue in a more comprehensive manner what we had just put forward as PBRISD, that should be the way forward for the industry. And that was under evaluation at the time by ICMM as to that going forward, and takes a little time to get all of their members on board, but was receiving serious respect. And just by, you said, well, why did I go there? Well, that's where the power to make change would be. And there were the people at risk, as opposed to going to ICOL and spending time in a committee that would focus, if you like, more on the minutiae of geotechnical practice, as opposed to the overarching policy issues that were central to honoring the safety requirements that we had. At that time, then Brumadinho came along. After Brumadinho, the industry lost its license to practice, which we had actually forecast in the analyses from Mount Polley, in which we said if there's another major industry, we think another major failure, the industry will lose its license to practice, and that's what occurred with Brumadinho. That led to the global standard, which was put in place, and here it is. We have no objections to honoring that. It's been an important contribution, and all members of ICMM, because ICMM was part of this activity, agreed to be participative in consistency with the recommendations of the global standard, which any of you who work in the business will undoubtedly know a little bit about. However, it's not enough, because it doesn't really incorporate the details of how to execute. It's good of what to execute, but how to execute, I think, is handled more effectively. The next slide, please. In the ICMM Good Practice Guide, that I had a fair amount of involvement in assisting its development. So ICMM then took on the initial recommendation of developing a good practice guide for tailings management in its totality, honoring the concept of performance-based design, but much more honoring the requirement for a safety culture and all of the empowerment of executives and so on, review at various levels. And this is an excellent document of how to achieve the safety that the global standard wishes us to. Next slide, please. Just to indicate some of my background here, the paragraph in the upper left comes from the Mount Polley investigation that I was part of. Tailings dams are complex systems that evolve over the years. They're also unforgiving systems in terms of the number of things that have to go right. The reliability is contingent on consistently flawless execution and planning, in subsurface investigation and analysis, in construction quality and operational diligence, monitoring, regulatory action, and risk management at every level. All of these activities are subject to human error. I'm coming back to the human error being the most complex and challenging part of managing uncertainty. Let me point out that this emphasizes that tailings dams are not the same as water dams. I don't agree with the tendency to put them in together in ICOL or elsewhere. The requirements of tailings dams is much more complex for those of you who work in that industry, and I hope you'll agree. I won't go on to read the what's on the right. It also comes up to the need for the kind of performance-based design that I've talked about, which ICMM has gone to some degree, has absorbed in its recommendations, we'll see in a moment, and indicated how to execute it. Next slide, please. So this is the elements of the tailings management. I talk about a system, and this comes out of the Good Performance Guide, indicates the implementations of a tailings facility life cycle system of what we have to manage, and you'll see things that all of the elements that I've talked about, but they're interactive. You go from one to the other, but you return in some instances, and you're in a process of acting and reviewing and so on in a continuous way. Next slide, please. The ICMM guide, the Good Practice Guide, also has this very nice cartoon that indicates the different ways in which we manage uncertainty from a prescriptive design base, that is the declaration just of a factor of safety or some tolerable settlement and so on as a hard number. Precautionary, in which is the observational method, which is our more common practice, and then goes on to honor and support performance-based design, and it's moving into risk-informed design, and it provides text on the right to expand the value of moving to performance-based design. Next slide, please. So this is then a flowchart of performance-based design. Select objectives, make measurements, observe performance, revise design, revise the thing is an ongoing, self-regulating, self-improving field chart for doing performance-based design. The performance is not just that it's stable, the performance is totally in terms of its pore pressures, totally in terms of its deformations. Seismic design is totally performance-based design. The factor of safety after the earthquake doesn't tell you how much it's moved, whether it's containment, whether it's cracked a lot, and so on. So the concepts of performance-based design are not so novel. It's the ability to integrate them in an effective and practical manner today that's novel, not because of the theory, but because we've got such wonderful computational skills. If we did try to do performance-based design 10 years ago, it would take you 6 months to get an answer. Today, you can get it in a day or two. So I think it's the integration with our enhanced capacity that makes it the way forward for meaningful structures. Next slide, please. Next slide. So the value of performance-based design, and this is taken from the good practice guidelines, spatially these are the things we have to look about, spatially complex and variable conditions, potential for strain weaknings, susceptibility for liquefaction, need to assess deformations, instability due to high porphyry. These are all interactive and all embraceable by performance-based design, and the desire to achieve robust design and maintain integrity to prevent failure. Next slide, please. Now, heading to closure, I want to talk about some examples to indicate that I'm talking about practice today, not theory. And I work a lot, have been for some time, with Freeport-McMoRan, a well-known large copper producer, perhaps not as large as Codelco, but certainly in the big leagues. And they are taking the practice to make public some of their integration of activities to achieve safety. I would say partly because we have a lot of large upstream construction, which are challenged by some who don't know enough, and we're content we know how to build upstream as needed where it's appropriate. Not saying you do it everywhere. But I want to draw attention to this report, Morenci Mine Tailings Disclosure Report. Morenci is one of the more complex, largest mines in Arizona, and they published this wonderful report about how they're managing their tailings in terms of local community engagement, the kinds of analyses that are done, and so forth. And they'll be bringing out other declarations of that, and it'll give you some comfort of how these things that I'm talking about now are playing out in the world of practice. Next slide, please. So this illustrates what's emerged within the corporation. Is taken from the Morenci report, indicating the evolution of the ability to be comfortable in terms of a good tailings management system. And you'll see in 2018, we were at the stage of formalizing risk-informed decision-making as an important vehicle to expand forward. And I'll leave that for you to look at. And these are all. This is from Morenci, but this is, if you like, the corporate history as a major player in ICMM and how they've got to a level of execution. Next slide, please. this illustrates, Morency, you can see the current large active tail is on the lower right. The number of them are closed. There's a community that you can see in the upper right that has to be reassured that those facilities will not fail and flow into it. And we're just in the middle of looking for a new site to expand production given the high price of copper that exists. So this is a very complex, large facility that's executed. And you can read what they've executed in their excellent tailings mine management system. Next slide, please. So heading toward the end of this presentation, it's an advocacy for performance-based design. And instead of my advocacy, I've chosen here to repeat the conclusions from a very senior consulting company who published this paper in Tailings and Mine Waste a couple of years ago. Key parameters are predicted to be measured, monitored during construction. If performance does not match, the model is updated to evaluate sorts of deviations. If deviation is significant, the potential failure mode, design methods are updated. Monitoring extends through entire life facility. Consider what may exist, use the best knowledge and simulation of uncertainties to generate the range of reliable predictions, requires judgment of what constitutes acceptable behavior under various loading conditions, verifies behavior with observational concepts. So this, if you like, is a restatement of performance-based design from my early statements from practitioners using it on major projects today. Next slide, please. Power of this method is that through model calibration and validation during construction, we increase confidence and reduce uncertainty in the design. So this has been a lecture about uncertainty, and this is why I was happy to have departed from, I'm not against probabilistic studies in terms of the sensitivity message. Here is where the ability of numerical methods to improve safety is clear to my ability to reduce uncertainty in design as opposed to worry about the probability variation. You can do sensitivity analysis. I'm not arguing against that. Next slide, please. So my journey from certainty to uncertainty in 64 years ends up with a positive outcome through the advocacy of performance-based design building on advances in computing power, software, and instrumentation to allow real-time response monitoring and modeling. In this way, numerical modeling has an integral role in enhancing our prediction abilities and improving the safe design, construction, and operations of geotechnically sensitive facilities. Final slide, I think. On this journey, I've been accompanied by an inspiring group of colleagues, assistants in graduate studies in my academic career, and from an equally inspiring group in my consulting career. And to each of them, I wish to express my appreciation for their guidance along the way, and my appreciation to all of you for being so patient if you're still with me. Thank you very much.
Okay, there you go. It took me a little bit to find the button. Professor Morgenstern,
yes.
Thank you very much. I will stop the screen. Thank you very much. It was a beautiful presentation.
Thank you.
Highly complex, very informative, particularly for professionals, because this is a topic of utmost importance nowadays, not only in mining countries, but around the world in general. And what I am thinking is that I'm thinking in the future that when we are professionals, we really appreciate this kind of talks because sometimes there are so many complex topics and so many complex concepts that and it takes time to understand them fully.
64 years.
That's my point. I mean, it was beautifully presented, and I on behalf of University of Chile, the Geotechnical Engineering Group, our students, our colleagues, I thank you very much for this beautiful presentation.
Thank you.
I really enjoyed it, and I'm sure our colleagues enjoyed it too. And I wonder, I will try to connect the two screens. I'm with two screens here. And I wonder if there is any questions
Yeah, we're happy
from either colleagues, professors, practitioners, students that might be interested in sharing some experience or a question for Professor Morgenstern. There is a question in the chat that asks if the presentation can be available. I have your presentation, Professor Morgenstern, but if you allow it, maybe I can share it.
Yes, by all means. Yes. I think you've videoed it. You've made a copy, haven't you?
Yes. I have we have all the information, and we also I will move this here.
Yes.
We have all the information, and and the video is will be on YouTube too. So I wonder if there is any colleague that would like to ask a question to Professor Morgenstern. Chileans are very shy in Zoom. Matias Ignacio.
Yes, I would like to ask something to Professor Morgenstern.
Of course, Matias.
Well, yes. Well, first of all, I would like to know if there's like a standard procedure regarding how to evaluate tailing incidents. I'm asking you this because I was researching about what tailing incidents are and what they mean. And I mean, before this talk, I didn't know really what tailing was. And researching it, I found out that it's very dangerous that these things collapse. So kind of my question is, what are there standard procedures to avoid these kinds of disasters, or is it something that goes case to case?
Well, they're not standard procedures, but I've just described the kind of system that has to be applied to avoid the disasters. The important point is firstly for owners it wasn't too long ago for those of us who work in the mining industry to know that tailings dams were simply regarded as waste, and therefore they weren't given any respect and weren't given any resources, were regarded as a kind of a minimal cost activity, a cost deserving only minimal resources. So I think we've now overcome that because the global standard and the insurance companies and everybody else now insists on a high degree of standard. So I think the resources to do things, the methodology we put on forensic investigations, I feel like the way to avoid things are to be compliant with the global international standard, and the good practice guide will give you the basis to avoid these things. But that requires a culture of understanding within the company and within the consultants that serve these things. Also, with the regulator, we have some problems. I think we have some problems getting the regulatory community up to speed on evaluating performance-based design as opposed to factors of safety and simple things like that. And we're making a special effort here in Canada to do that, and they are in the United States as well. So I think that because regulation isn't in different ways in different countries, is something that your community may want to think about with your regulator, what they need to do to be comfortable in evaluating performance-based design. but certainly all the procedures in words are all documented. What I've referenced, the issue is to learn how to execute them.
Thank you very much.
Thank you very much.
Professor Norbert.
Thank you very much, Professor Morgenstern. Thank you very much, Matthias. Professor, there is a question here from Mariel Rodriguez, and she asks, what was the most challenging project you have worked on? What lessons did you learn that you could share with young engineers?
Well, I think the most challenging projects have been projects with weak rock foundations that have these low strengths, whether it's a hydro project or whether it's an oil sand mine, and so on. I'm just involved. We're just finishing a big hydroelectric project in British Columbia that also has weak shale foundations, and they're extremely demanding and require a lot of geology to understand. I think if you're wanting to know a guidance, because we become a little poor in our educational system, to think through is to have a greater understanding of the geological circumstances in detail than we're accustomed to. I think part of our educational system has tended to reduce the need to understand geological hazards in a detailed sense. So I think the difficult foundation conditions, whether it's one dam or another, are the most challenging. Sorry, there are a bunch of some other figures, questions are popping up on my screen, but I think you'll have to capture them.
Oh, sorry. Do you want me to share again?
Well, they come and they go, but I think you'll have to find the question to ask. No. Questions are coming up on my screen.
Right. Yes, I have the questions here. Yes. I'm going in order.
Okay.
I have a question here. We had the question from Michelle. If I am missing a question before me, Mariel, please let me know. So I have a question here from Alpha Umaru Yalo. How can the ICMM enforce compliance of its guidelines to mining companies across the globe? That's a tough one.
The ICMM can only the ICMM
suggest, I guess,
has no enforcement capacity other than its members, and you have to be a big and relatively rich company to join as a member. So that the enforcement comes by example, and I expect, for example, we have situations in which companies now, I know one large gold company that is not a member of ICMM, has to now explain to its executive why they should enforce these guidelines, because their insurers are asking about it. So it's a question of education to understand what is needed in a company to do the right thing. But ICMM has no enforcement capacity other than by example.
Yeah. In general, it works like that. With other types of institutions.
There has been an obligation for all of the ICMM to do risk analyses of their major tailing structures. And all of these risk analyses are now going to be in the public domain. So I think that this excellence by example will have its weight in the investment community.
Very good. Thank you very much, Professor. We have another question from Andres Orozco, and he asks, which would be the key reasons on why tailings dams require a more complex analysis than water dams?
Tailings dams are more complicated than water dams by virtue of their
absolutely
by virtue of their incremental construction, the changes that have to be made, the propensity for liquefaction in the tailings, and so on. So I believe the tendency, even in some agencies in Canada, to have the same guidelines for water dams, same standards for water dams and tailings dams is fundamentally wrong. It doesn't respect the complexity of a tailings dam.
Good. Thank you, Professor. Some of the last questions. Jimmy Ochiro, he asks, in the first case history that was presented about the deep excavation with continuous movements, what was the countermeasures that were used to complete the excavation and the project?
The continuous movements, the project was completed accepting the continuous movements because the factor of safety was sufficiently high that it may well have reduced from 1.8 to 1.4, but I was happy that I could live with the stress, but I thought it would be fine in the end. Had we been at 1.5, which might have been an acceptable standard, we would have ended up maybe at 1.1, and then we would have had to stop construction and do more anchors and something very, very, very challenging. But we had a reserve resistance, not by design, kind of by accident.
You mentioned something there very important. It's important for us to sleep in peace, to go to bed in peace.
That's right.
Yeah, that's very important. Thank you very much, Professor. There is another question from Matias Bravo. And Mr. Matias says, in my master's studies, I investigated the influence of relict structures or discontinuities on slope stability of granitic residual soils, and I continue working on the article. In your experience, what do you think is the greatest difficulty in the stability of residual soils? What methodology or literature do you recommend to address this problem?
Well, I first went to spend time in Brazil many years ago to try and answer those questions because I didn't have enough experience with residual soils at the time, going back now 50 years, I guess. So there are several major issues. Firstly, there's of course unsaturation and the implications of changes of suction and so on, unsaturated flow, which is well understood. And I think we understood that in a crude way in Brazil a long time ago, and even but the details of that needs better understanding. But the overarching understanding is the variability associated with the product of the weathering environment. You might remember the Cadia failure that I showed the picture in Australia. Now the Cadia, if you take, I don't know if the final report is in the public domain, but it's all well understood now. The designers of that dam were very famous world-class engineers. And the design of the dam went through 6 or 8 or 10 lifts. It was, you have a lift and it goes to somebody to put on a lift and so on. But the early investigation of the foundation recognized a weathered environment, which is common, and there were some clay zones. They took the clay zones in the weather environment and remolded the material and said, this is the weakest strength we can have. We're not paying attention to anything else in this material. We're going to take the remolded strength. I think if I'm repeating this correctly, I may be missing some details now. But that wasn't the case. When you have an environment of such weathered complexity, there may be a weathered zone which is not remolded, but is collapsible. And so that you find that you get to a stage and now you've saturated it, you built a dam, and suddenly it collapses. I'm not talking a huge collapse, enough to create shearing, and you're holding up a pile of saturated liquefiable material. That was the mechanism of CATIA. Now, how can you find that? You're not going to have investigation to deal with that complexity over such a large dam. So you have to have a way of validating your foundation incrementally. You have to have a checking process as the foundation is revealed as you build the dam incrementally. You build it over years. You have to map each square meter of the foundation and say it's consistent with the design base, or we have to make change. And that kind of variability is particularly acute in weathered environments. So complexity requires ongoing checking and validation, and either validating the original design-based memorandum or changing it. That was the root cause of CATIA. Wasn't done. And it's very rarely done until recently.
Thank you very much, Professor. I think the questions are over, but it seems to me that we have one last. No, it's not a question. It's a warm regard from guess who? Luis Valenzuela. Luis Valenzuela.
Wonderful.
Mr. Valenzuela says, please give my regards to Professor Morgenstern. I was very pleased to see him now on the screen. So
Well,
he is sending you a lot of regards, and also Mr. Matias Ceballos from the university, a well-known university in Concepcion, to the south of Chile. A lot of people was here with us tonight watching this presentation, Professor Morgenstern.
well, that makes me
It
very
seems
happy.
to me it seems to me that there are no more questions. Mariel, she was joining us from Brazil. It seems to me that Nilo Consoli, I saw that Nilo Consoli was also from Brazil here joining the presentation. And we have many people from around different places. I'm looking this way because I have you in this part of the screen. But Professor, it seems that there are no more questions. I might have one last question regarding it's a question that I would like to ask as a professor. After so many years of practice, of seeing how geotech is performed around the world, from teaching different professionals from everywhere, from your impactful research, your consulting, what would be your advice to the education, to the education regarding geotechnical engineering? What do you think would be the most important topics that nowadays, with all the new concepts, all the new engineering that it's proposed around the world, what our kids should be, our young engineers should be learning these days, in addition or instead of what we usually teach?
Well, the greatest lack in current geotechnical education, and we do our best to repair that at the University of Alberta, but it's hard to do, is getting an understanding of the right level of engineering geology. Everybody is certainly happy in learning mechanics and learning finite elements and flak analyses, and all of these things are becoming easier. Hopefully, we're making sure they understand them and so on. But to understand where uncertainty comes from, from the ground, first of all. It's hard to get in the classroom
Mhm.
uncertainty from policy, from management, but one should at least make uncertainty from the ground, different environments, different degrees of variability, different degrees of strain weakening, and so on, a central part of a geotechnical academic program, because that embeds the concept of uncertainty and makes one understand that analysis is a servant of uncertainty, not a master.
Yeah, I agree. I agree. I
Yeah.
agree. We should emphasize. I like geology a lot, and I can resonate with what you are transmitting here regarding the importance of geology. It's very important, geology, and it's not only important, it's also beautiful. So it's
That's
very nice to study geology. It's very nice to study geology, yeah? And I totally agree with you, Professor. Professor, it's been a wonderful time. I have no words to express our gratitude
It's been a pleasure.
for the 2 hours, that more than 2 hours that you spent with us. It's a privilege for us to learn from such an impactful. I will stop sharing because I'm looking all everywhere. So
Well, it's now time for me to go and have a glass of red wine.
yes. It's a good call. It's a good call, Professor. Thank you very much
Thank
again
you all.
on behalf of our geotechnical engineering group. I look forward to meeting you in person sometime soon.
Thank you.
Say hi to our colleagues at the University of Alberta, and also thank you very much, not only to you, but to them, to Vivian. She was very kind and helping us with all the preparation of the presentation.
Thank you.
And thank you, everyone, all the people coming here today. I really appreciate the time you put into coming here. So thank you, Professor Morgenstern. Thank you very much. And
Bye-bye,
have a good night.
everybody.
Thank you, Professor.
Bye.
Bye-bye.